Hey Nick, how are you doing? I had the microphone off. I was like, oh no, what are you up to today? How's everyone doing in the chat? Might talk a little bit about 320 here, or what do people want to know? Because we can kind of do some crossover work between 320 and 201. So we can talk about regression, which is the next chapter on the next test. Mubot is awake. Let me reset Mubot. How is he awake? How is Mubot awake? We're going to reset him right here. And then we'll probably talk some regression because it's good for both classes. So like kind of an introduction to regression. Let's go to 233. So stat 201 / BS 320. Introduction to regression. And if you're here, say hey in the chat and tell me how the test went or ask questions. We are here to take questions, answer questions. Let's go over here to the main screen and talk a little bit about regression. Okay, so we have to know what regression is first. Like, what is regression? Regression is when we have two quantitative variables. Now, there's a data set I really like right here called the cars data set or the empty cars data set. It's, I don't know why it's called empty cars. We'll do empty cars question mark. And so it's going to tell us about it. Motor Trend Cars Road Tests. So Motor Trends comes from, I think it's a magazine right there. Yep, US magazine, so 1974. And they've got different variables right here. This is what the data looks like. You got miles per gallon, you got horsepower, you got the weight. And you would think something like the weight of a car would be negatively correlated with miles per gallon, and you would be correct. So we can easily go right here and plot this. You know what I'm gonna do? I'm gonna go to attach. This makes life easy. So, yep, there we go. And we're gonna go right here and go to plot miles per gallon, comma, weight. And there it is right there. So you can see the miles per gallon. We'll reverse it. Just plotting the two variables right here, and you can see a negative. There's a little bit of a non-linear, it kind of bends at the bottom right there. But what's even better is we can actually make a linear model with this by going to LM, and the Y variable of interest, we want to predict the miles per gallon. Oops, forgot my parentheses. Weight, and we're going to do data equals to be nice, the empty cars data set. Hey, Courtney, good to see you here. So this is the linear model right here, which has the conditions QQ straight enough, no outliers, plot doesn't thicken, which we'll be covering today in class. This is the linear model, and you notice the line does pretty well, but it starts to bend. We actually have a way of looking at this really easily by going to choose order, and you can see the line has a little bit of bend through there. I'm going to put to max order equals 2, so we don't get too much. And you can see kind of the bend where it's bending towards the end. It's a little bit nonlinear, and this fits a polynomial model, so we can kind of check for nonlinearity. And there's lots of tests to do these sorts of things. More specifically, we can do the check regression right here. And we can see if there's a problem with the linearity, and there is. And so what is that right there? What is that thing? We've learned about these quite a few times. They're really big on test 3. So what is that thing we see right there? What is that thing called? That 0.0112, which allowed me to say there is evidence of nonlinearity. Because we start out assuming there's linearity, and then we have evidence of non-linearity right here. So what is that? What is this probability thing called? It is a what? What is that probability thing called? We'll see if anyone says it in the chat. We'll throw 100 points to start, and we'll see if anyone says an answer right here. That thing right there, that value is a p-value. That's a probability right there. If we see, given there's a linear relationship, and we would actually say it looks like what we see in this data is unlikely given the data is linear. So we are saying we have evidence of a nonlinear relationship. So we should probably, if we really wanted to, go in here and fit the nonlinear. So you have to go to poly. If we really, oh, not that. Poly, we were doing weight, and you have to do to the second order. And now, I'm not that good at visualizing these, but there's the visual of it there. And we actually explained almost 82% of the variation with the R squared. And that's increased. Did I actually look at the other model? I didn't. So let's see. Or I thought I did. I've got the code right there. The original model, we'll go summary of M, and then M2, and summary of M2. The original model explains 75% of the variation. The new model explains 82% of the variation. And actually, we could have gathered this kind of sort of from here, but that's the R squared adjusted of the model, which is the R squared after we take into account how many variables are in the model and give ourselves a penalty. It's an R squared adjusted for how many variables are in the model. But the key note, especially for 320, is interpreting all this output. Which exam question are you wondering about? How did the exam question go? And I can kind of go over that. This is regression right here. And we can do regression inside of jump also. We've got right here a data set, and let's go do a regression inside of jump with fit y by x. Height explaining weight, or let's reverse it. We'll put weight down there and height up here. And now we've got a model. Ooh, this is survey 10 data. So I know this data set well, because is it? Looks like survey 10 data. And so we can fit the line, and you can actually see the nonlinear problem through this. You can do the same sort of techniques. Will we have access to your? You can if you want. I'd usually do those publicly, so we'll try to do a midterm review. We can actually fit the polynomial here like we just did in R, and you can see the polynomial model. What's really cool inside of Jump is it's got some interactive stuff right here where you fit a, is it fit special now? Let me remove these fits and try the fit special. Because you can do like a bendy fit. I have never fit that before. It's not what I wanted. They might have changed their fits. Fit flexible, fit spline. There we go. I'm going to try this. Yes, there we go. A little bendy line. You got to be careful, though, because you can overfit, but we can really see the non-linearity with this now. You can see how it kind of levels off up here. And so if we go back and fit the line again, you can see the non-linearity compared to the line. And these are the kind of the key things to notice is that the line can only go in one direction at all times, or rather, it has to stay on a line. It's still monotonic. Was number 24, what percent? Yeah. So a question like that right there, if we were to mimic a question like that, we could ask, so let's go here, go to gender, and we'll write a similar question. We'll go, so try answering this question. Let's go to the contingency table. And let's say, what percent of students have broken a bone of the males? So let's say, what percent of students have broken a bone of the males? So, trying to do a similar sort of question. What percent of students have broken a bone of the males? What percent of students have broken a bone of the males? Might be right. Let's see. I think that's right. Right? So we go right here, and then we go of the males. And broken a bone. It looks right. 9 over 15. Does that make sense? So it's not what percent of students have broken a bone and are male. It's, you could rephrase it and say like of the males. So if you put of the males first, it might make a little more sense. But like what percent of students, or you could say like what percent is a totally different thing, of students live on campus of the in-state students. So this is the conditional aspect of it right here. Of the in-state students is kind of the conditional of it. And so when we say what percent of students have broken a bone of the males, that is the conditional to say of only the males right here, what percent have broken a bone. Does that make sense right there, Courtney? To do it this way right here, and then you're looking within this. Yeah. No, that's it can be tough. And then you have to be like, okay, so what exactly are they asking for? But the difference would be, like, if we say, what percent, this would be totally different. What percent of students have broken a bone and are male? Now, that's totally different. This one, what percent of students have broken a bone and are male? So this would be this group right here and this. That'd be 9 over 40. And that's only for this one here. What percent of students have broken a bone and are male? But what percent of students have broken a bone of the males? That is saying within the males, and you would only look at given someone is male. So that one is going to be this right here. So the other one uses the full table and uses kind of a cell. There's a really good My Pearson one. Like sometimes I'm mean to My Pearson, but there's a really good My Pearson question that goes over the subtle differences between things like what percent of students have broken a bone of the males, what percent of students have broken a bone and are male. So there's very subtle differences on the wording right there, but the key being of the males would narrow it down to a conditional. So the and is, the and are male. Like what percent of students are this and this Well, that's not saying like of the males, because you could rephrase it like of the males, what percent have broken a bone. So you could also say what percent of students have broken a bone. Of the males, what percent of students have broken. So it makes more sense kind of if you throw this at the start and say, of the males, what percent of students have broken a bone? But of the males, maybe a little grammatically hard right there, I do admit. But we weren't trying to be tricky. It's just sometimes, you know, the way people say things can be a little confusing, but still totally of this group, what percent of broken bones? Yeah, exactly. And that's why, you know, there's no perfect questions because especially sometimes people like are reading things different ways. So there's no perfect questions, but good question right there. God, that makes a little more sense. But the key being like have broken a bone and are male would be all students. And then what percent of students have broken a bone of the males would be of the males right here. What percent have broken a bone? So probably better way to read it right there. Yeah, what other questions are there? Feel free to ask them. I can go over some stuff right here. We got a little bit of time before class. But what are you thinking? I love doing some regression. We should mark that part of the video. Other people might be wondering. So here we go. That was about 7:53. Stat 201. And that was conditional distribution test questions. And we're back here for regression now. Stat 201, BAS 320, regression. So what is the point of regression? Like, why do we use regression? Why do we use regression? Like, what is the point of doing regression? To do what? We see it over here in Jump, and we see it over here in R. You can do it in any sort of software. You can do it in Excel. What is the point of regression? What is the point? We're kind of just doing some review of regression right now. What is the point of regression? What does it mean to do regression? Yeah, that's it. Yeah, no, Courtney, that's it. Regression is fitting a linear relationship to two quantitative variables in its simplest sense. That's a lot of times we might even call this simple linear regression. There are advanced things like polynomial models, multiple regression. There's so many advanced things you can do, but in the simplest sense, seeing if there's a linear relationship between two quantitative variables, which is why we have the conditions of QQ straight enough, no outliers, plot doesn't thicken. So how do you know it's QQ? Well, it's two quantitative variables. That's what QQ means. We have weight is quantitative, miles per gallon is quantitative. Good. Straight enough. This might be a tougher one. A really easy one to see is not straight enough is going to be this one because the bend at the end of it, which we were just showing here a second ago. Oh, I can't make it reappear. Can you explain to me what plot doesn't thicken mean? Really good question right there. So we got a really big technical term for this. The really big technical term for this is called heteroskedasticity. See, it's a word. You know what's interesting about that? And I'll explain what this means in a second. Heteroskedasticity is also a word. You can spell it with a C or a K. So there's heteroskedastic, and then there is homoskedasticity. What do these words even mean? Okay, we're just talking about the condition here of called plot doesn't thicken. Plot does not thicken. Okay, what does hetero mean? What does hetero mean? So what does just hetero mean? Does anyone know what hetero means? Different. And homo means same. So we have different and same. So when we talk about something being heteroskedastic, heteroskedastic looks the following way. This is a heteroskedastic plot. A heteroskedastic plot has difference in its whatness. This is heteroskedastic, and this is homoskedastic. You don't got to use the advanced words. They're just fun to say. This is sometimes called equal variance. We want there to be equal variance. Sometimes it's taught as the equal variance condition. So what do you notice about the heteroskedastic plot? And what do you notice about the homoskedastic plot? So the heteroskedastic plot has a plot that thickens. It thickens in areas. It's not that it gets thicker. Yeah, different distances, different strengths. So the reason we don't want the plot to get thicker or thinner is because it denotes a differing strength, where up at the top it's stronger, and down here it's weaker because it's further out from the form. So we talked about the form, and the tightness around the form is the strength. So that has a differing strength or a differing thickness, where this one is pretty much the same. Like we could say moderate throughout. So if you're going to use things to describe it, you don't want it to change throughout the plot and get weaker or stronger. So what we want is we want the homoscedastic relationship. We want homoscedasticity because we want what? Why do we want what is called homoscedasticity? Why do we want homoscedasticity? Which you can call it plot doesn't thicken, which is the answer to why we want it. So why do we want that? And tell me, Nick and Courtney, does that make sense? So I've used some technical terms right here. Well, not that it makes it stronger. We want the same consistent relationship throughout. So we want the same sort of strength throughout. We want it to have, if it's strong, it stays strong. We want it to be the same, like we don't want it to get really strong in one spot. Consistency is key. So we want it to have the same sort of consistent relationship. So overall, this plot right here, I moreover see outliers and nonlinearity. This is what I was trained to do. So I was trained to draw on all plots by Dr. Seaver. That's what I used to do. I mean, he would say, I need you to draw on them and turn in your drawings. So what I would draw for this is I would immediately start denoting we have some mild outliers over here. So there's our outliers. And then we also have a bit of a nonlinear relationship right there. So we got some nonlinearity. And then when it comes to the strength, I would say the strength looks relatively constant. There's fewer points at the end. So overall, there are some outliers. There's more evidence of nonlinearity. The strength, as far as I can tell, is rather constant. So I would say the biggest problems here are the outliers and the nonlinear relationship, because outliers can do anything to regression. They can make it positive, negative, stronger, weaker. So we don't like outliers. We QQ straight enough. No outliers, plot doesn't thicken. You got to be careful. You don't want to say the plot is getting really thin right here, because that's just 1 point. Lost points with Dr. Me on that one. We want to say over here, we really don't have a good idea of the strength of the plot because we only have 1 point. We understand the strength of that. We understand the strength of that. And I'm talking about how spread out it is. And if you look, it's relatively similar thickness throughout. I know you might be saying, isn't the thickness here that? But we only have 2 points to gauge it. So overall, where we have the majority of the data, we do understand the thickness, and it's relatively the same strength. So once again, we are going for a homoscedastic relationship, which is plot doesn't thicken. You don't need to know those advanced words, but I do like them. They are neat. This plot right here also shows homoscedasticity, I would say. It might be easier to show it right here. The big problem with this one is the nonlinearity of it. So if you look at the strength of it, you would go right here and do the following and say it looks mostly the same strength, but it looks like it has a bit of a nonlinear. So do you see how it has mostly the same strength right here? There's not really outliers. The big issue with this one is the nonlinearity. But I would say throughout this, it stays about the same spread from the parabolic relationship that it has. And once again, we can do this via the choose order and kind of see, ooh, wow, pretty close to what it is, right? So there is the order right there with the polynomial. And I should get better at fitting those. How do we fit those? I'm cheating and looking at Dr. Petrie's code. It's actually not that hard to do. Where's he plotting it? Here's where he's plotting it. Lines, fitted, line width. Oh, he does the poly. Oh, it's just this? Okay, wait. There it is right there. So the model with the X and the Y, and he does lines with fitted. Okay, so if we take the lines of the variable, so the variable's weight, and the fitted model, and then he's got I equals 2 right now, I think. Oh, it also fit that other line. It's the colors. Why am I getting both lines? Well, I'll be. I'm so close. This is the Y variable, which is horsepower. Sweet. I just want the one line. I just want the one line. Well, hobby. What questions do we have? I only want the one line. I just want to see the polynomial model. Oh, plot new has. Okay, so it's going to add the plot. Okay, I got it. That's what we got going on. Let's go over here. Nope, that didn't do it. So close. Look at Peaches' code again. Look at his code. Well, it makes sense that that would run. There's the plot. Okay. He called the plot, and then he added it on. So it should work, because I've called the plot. We called the plot, then he made the model, then he added it on. Shouldn't matter that much. Didn't do it. Lines. Lines, lines, lines. That's the fitted model. If you have questions, let me know. I'm just going crazy over here. Let me look at it again. I just want to make the plot, and I've done it before, like looking at his code. It's not where he's making the code. Plot of that. Oh wait, X lab, Y lab. That's fine. That's just class Y lab notes. Max order. That's fine. Well, let's just take the code right here. What's he storing? Versus return. Return. He stores it all into D. How to interpret the intercept and the slope again? Yes, Ivan, that's for 320, right? So interpreting the intercept and the slope. So when you think about this model over here, let's go ahead and make the linear model again. I'm just going to stop doing this right here. When we interpret, and this is for 320, we need to count this for 201 also. How would we, well, first off, what is the intercept and what is the slope, Ivan? So let's mark this part of the video, interpreting intercept and slope, 320. So first off, what are the intercept and the slope? What are the intercept and the slope? So what are the intercept and the slope? What are they value-wise here? So we need to be able to tell the coefficient of the intercept and the coefficient of the slope. I think there's a way. I think you type coefficients right here. Oh, look at that. So what's the coefficient of the intercept and what is the coefficient of the slope? There might be a way. Let me see here. Show regression equation in R. There might be a way. The LM, I know that. Might be, I'm always looking for new codes. So it's really fun to look up new codes, find out things that can be done. Ooh, what is this? Stargazer? We're finding new packages as we speak. So 320, tell me what's the intercept? What is the slope? Yep, intercept and slope respectively are that. There's a new package or something right here called Stargazer. No idea what it is. We're going to load it up here and see what we get with the Stargazer library. Another really good option for creating compelling regression and summary output tables is Stargazer. Ooh, so let's see. Here is the Stargazer thing, and we've called our model M. And, oh, type HTML, we don't, ooh, no, we don't want that. Type, what is the type available on this? Let's see here, F1. And the types are what? Type LaTeX to begin. So it's going to do LaTeX, LaTeX by default. So it's not actually printing it out yet. Let's see what other types there are. LaTeX, text. Okay, so we can do text. So type equals text. Ooh, not too bad. I mean, Let's see. Let's bring this over here into an RMD file and see how it looks. And we're going to look at interpreting this. So we're going to try to make this look nice and pretty here, which is always our goal. There's so many ways to do these things. Random work. Okay. So we are storing this right here. And let's remove a bunch of this stuff right here, which we're not going to include. Boop, done. And then let's add in a chunk. And no, we don't want to knit it yet. We just want to add in a chunk. And we'll call this regression. Well, we'll go startup. And for the startup, we need our libraries. So we got library Stargazer, and that's the only one we're using right there. And then we want to go and add in another chunk. And let's say regression. And now let's grab this right here. So we need to make our model. And then the Stargazer library looks to have a good way of summarizing it. So here's the Stargazer output right here, which is not including the header on the table. It's a type text. Let's go to LaTeX, however it's said, and let's go ahead and look at the visual of this, see what it looks like. Here we go. Is it going to show me the output? Ooh. Well, we're going to have to knit it to see what it looks like. So let's go ahead and knit this, see if we like it. Knit to Word, and let's call this regression check. Okay, so it's knitting. Should knit. You gonna knit? You gonna do it? There we go. It's starting the knit. And so Stargazer looks to me like it could do really nice output. Okay. Ooh, no. Okay, that's no. HTML. Knit again to Word. See what it does right here. No. Which we could probably instead knit it to HTML. I think I have it set to allow you to turn HTML documents. I want to see what it does for HTML here. See if it actually looks any good or what it does. Here's the HTML. Really? Well, I'm shocked. It's still not showing up right. So it looks like we have to actually go right here and do text. So we are going to go with the text option right here to interpret this. Speaking of regression, have we done a help video on data analytics? Yeah, we could do that here soon. Yeah, we got time. Good question, Sloan right there. So we're going to knit this again to Word and see if we finally like this. And this is what you generally do is you make sure you get what you want, because right here, I might delete. I never like the way, I'm not the biggest, all the comments right here, all the hashtags, it's not the prettiest. I mean, it's looking pretty good. Is that the standard error below it right there? We'd need to check the output and see if that's the standard error. Let me see if I can find something a little bit better, and then we'll interpret these. I don't love how that looks. Tidy can do it too, it looks like. So we should have tried with Tidy instead. Okay, so Tidy, let's load up Tidyverse. Not liking how that looks. Okay, so let's go here to library, Tidy. TidyR should do it, or Tidyverse. I thought Tidyverse needed to be loaded up. So let's go here, really, and do Tidy. Where's Tidyverse? What is Tidy a part of? Tidy is inside of which library? Oh, is it dplyr? No. Where is Tidy? Tidyverse. And that should load up everything. Where is it? Well, I'll be. Tidy function in R. Tidy function is in Broom. Of course, I remember that now. Broom. Okay, now we have Tidy. Okay, looking better. And that's a tibble, which I'm guessing, because it's a tibble, tibbles are, we can probably just go right here and do our really good output on this. Let's go to library flex table. And with library flex table, we might just be able to put this in a flex table. Yeah, look at that. There we go. And I think it's, I always forget, I've done this so many times now. It should have the ability to round, and I always forget how to round a flex table. But we could probably go right here and go to round on this. We could round the tibble before we put it through there and do that, and it's not liking it. Really? We can't round the tibble? Oh, It's mad about that because there's words in the tibble, I think. Let me do one more thing right here. Let's make sure we round our data to look nice, and rounding in flex table. You have to do things multiple times to remember how to do it. Digits, it's just digits. Oh, it's column format. So I think we have to pipe it through a column format double and say digits equals 2, and there we go. Look at that. Look at that. I don't want all the columns to be formatted that way. So let's go here. The I equals 1. Let's try that. Okay, that's the rows. So we want columns 1 through 3, I think. There we go. And the p-values on the last one are a bit ridiculous. Ooh, we don't want p-values like that. So we're going to pipe it through another column format. And we'll just format that 4th column right there to have 5 decimals. And, oh, no, the 5th column? There we go. And then this needs to be 4th. There we go. And, yeah, digits and big decimal. It's basically 0. P-value is basically 0. How's this looking, Ivan, right here? We now have a much better output for our report. We just took the model right here, and we have the information needed for it that we can present to somebody. We can also pipe this through a theme. If we want to do theme Vader or something like that, we can make it look like this or however we want. But the goal here is to make the output look nice. We see what the estimate of the intercept is. We see the standard error. We see the statistic. We see the p-value. But this is going to look nice and neat in a report right here for somebody to easily read. So always be thinking about, how do I make this output look good? How do I, you can save the picture now if you want, or you can just put it into your report, but make the output look good, make it look professional. And we might even look at a few reports tomorrow if people want to show examples of their reports, because it should look like something almost in like a scientific journal. Theme Vader might not be the best for that. There's other themes if you want to use. But what does this all mean? And actually, Sloan, that was the wrong theme because it's the wrong package. This gets into Stat 201 because with Stat 201, we have to know how to interpret slope and intercept. So what does this mean right here? Let's go to, is it par and flow? Parameters. Yep. And flow. 2 seconds, and I am going to make something here for you to see. Oh, it was in the choose order. So I need the par and flow. Where did Petrie do that? Here it is right here. That's what I was looking for. Okay. So many codes I use so often that I forget how they work. Rows and columns. So I want 2 rows, 1 column. Remake this right here. That's good. And then visualize model of M. Darn it, really? Oh, well, it's not letting me put them both on the same plot. It's a real bummer right there. Let me try this. Plot of MP miles per gallon, or weight, horsepower, and weight. Miles per gallon and weight. Well, you can't get them both on the same screen at the same time. Okay. So when you look at this model right here, so here's the big things, Ivan. When you look at this model, what does, and we'll take a screenshot of it. Oh, because it's in the viewer. That's why. What does the intercept mean? When you look at this model, what does the intercept mean? So Sloan, this is a good thing too right here. This is Stat 201 right now. What does the intercept mean? What does the intercept mean? How would we interpret that intercept? What does the intercept mean? That is the estimate of the intercept. In notation, it is known as B0. This is for Stat 201 and 320. This is actually doing data analytics number 5, regression right here. So both classes are being covered with this sort of material. What does the intercept there mean? And it looks the exact same way inside of jump. If you go to the jump output, you get the estimates right here. I'm going to show them side by side. If you look right there, you have the intercept and its estimate, the standard error, the statistic, which is the t ratio, and you have the p-value. So this is the exact same things inside of jump. So you have the estimate of the intercept, the estimate of the x variable, the standard error, and all that information right here inside of R Exact same way inside a jump. They might call the t ratio the statistic, but so it's the t statistic, but that's what we have going on. But what does that estimate mean right there, Ivan? I'll answer it here in a second. But the intercept, which is off the graphic, which would be an extrapolation, is the estimated miles per gallon or the predicted miles per gallon of a car that weighs 0 tons. Now, the problem is cars can't weigh 0 tons. And you see this right over here in the data that there are no cars that would be this low. So that's an extrapolation of the model, and it is illogical to talk about the intercept. So the intercept is an illogical value because cars can't weigh 0 tons, and we really wouldn't make predictions right there. And so it is the point where it crosses the y-axis. That is correct. Or the x-axis, Sloan. It's when x is equal to 0. It's when weight is equal to 0. We would expect a car to weigh or have a miles per gallon of 300 or 37.29. If this blue line were to extend up all the way, it would go over here, and that's where it hits 0. So it really is not logical, and that's important for 201 also. That is not a logical intercept. But here's where, and this is very important for 320, what does this value mean right here? What is the interpretation? And the notation for that is B1. So what is the interpretation of the slope? And this is for 320. We have to be very exact in our interpretations. If you go to the notes on it, we have lots of practicing of interpreting it. If you get points off and do this interpretation in 201, let me know. But in 320, we are very exact on our interpretation. And the reason we're very exact is because think about height and weight. When it comes to height and weight, we know that weight is associated. You're on the right track, Ivan. And so think about this. What is the slope coefficient in this model? So you should be able to tell me, looking at the regression equation, what is the slope coefficient? Like, what is the value of the slope? The value of the slope is what? So remember, a linear model is the intercept plus the slope times the x variable. So what is the value of the slope in this model? And we're looking at R and jump output because we should know how to read any output and know where the values are at. Someone might have an output from Excel or Minitab or SAS or SPSS or NCSS, that is a real program, or Stata. So we should know what we're looking for. What is the value of the slope, and then what does it mean right here? Where is the value of the slope? So look at the information presented on the screen, and where is the value of the slope? Where is it? Where is the slope? That is correct, Sloan. You got 100 points right there. That is the slope. The intercept, which you nice and jump, you can trace it backwards. You can see the intercept is at 54.7, which is where it hits the x-axis. Now, in 201, we would probably say for each 1 unit increase in weight, we expect height to increase by 0.08. But here's the problem. We don't do that in 320 because we're very exact with our words. So we really, in 320, and this is something Petrie's made very clear, want to make sure we want people to know that there's not like a cause and effect. Well, people who weigh 0 pounds would be expected to be 54.7 inches tall, but that's illogical because you can't weigh 0 pounds. Does that make sense, Sloan, for the interpretation of the intercept? For someone who weighs 0 pounds, because it's when weight is equal to 0. So if weight was equal to 0, we would expect the height to be equal to 54.7. And that's illogical because you can't weigh 0 pounds. So what we really have going on right here, especially with the slope, is we're talking about the differences between individuals. As in, 2 individuals who differ in their weight by 1 pound are expected to differ in their height by 0.08 inches. Now think about this. If someone weighs 100 pounds more than you, then what would you expect the differences in your heights to be? If someone weighs 100 pounds more than you, then what would you expect? If the coefficient of the slope is 0.08 and there was a 100-pound difference between individuals, then how much would you expect someone to weigh more than or be taller than you by? Just think about how coefficients work, and if there was a 100-unit difference between you and someone else, then you would probably expect what? The differences in your heights to be what? Like, we had 2 people who differed in their weights by 100 pounds. I'd probably expect their heights to differ by how much? 2 people who differ in their weights by 100 pounds, I would expect their heights to differ by how much? Well, we could take this right here, and we're just going 100-unit difference over here. And so I would expect them to be 8 inches taller. And so 8 inches right here looks to be the difference between these two right here. Well, not 10, because remember the coefficient is 0.08. Good answers right there, Ivan. We'd expect them to have a unit difference of their height of 8 inches, because that would be 100 times 0.08. So you're just taking right here and doing 100 unit difference, and you would have somebody like, if you have someone who's 100 and 200, the difference between them is 100 units of the slope, and thus we would say we would expect them to be about 8 inches taller. Now, the thing is we don't want to make this sound like cause and effect. If you make it sound like cause and effect, I'm going to tell, I can't think of his name, Saxon, to take off some big points. Because if you say for each 1 unit of weight you gain, for each pound you gain, your height will increase by 0.08. It's not the way the world works. You can't just get taller by gaining weight. Yeah, exactly. So now you can see it's just a 100 unit difference right here. These people who differ by 100 pounds of weight are expected to differ by 8 inches in their height, because you would just times it by the 0.08, or the differences between like a 200 and a 300 pound person. The relationship at the end definitely becomes nonlinear, which is part of the issue. So with the model. But take a look at this. What does this mean for two cars that differ by 1 ton in their weight? Two cars that differ by 1 ton in their weight are what? So two cars that differ by 1 ton in their weight are what? Two cars that differ by 1 ton in their weight would be what here? So if we had two cars that differ by 1 ton in their weight, they would be what? And these are the key interpretations, the key things to practice. Two cars that differ by 1 ton in their weight are what? I'm going to give this a moment more. This is the key practice. Like, I can say it a bunch of times, but until you start writing it down and practicing it, then you get prepared for the test, especially for 320, where you'll have to be interpreting output. So I can say it a ton of times, but you have to be able to do this. You have to know what it means. When we have two cars that differ by 1 ton in their weight, we would what? Well, you're on the right track, 5.34, but what is that? Well, that's the coefficient of the miles per gallon. So two cars that differ by 1 ton in their weight, what does that mean for miles per gallon? So if you look right here, you've got car at here and car at here. They differ by 1 ton. So this is 1 ton difference. So what does that mean? And Mary, you said negative 5.34. So what does that mean? And these are the things you have to look at and practice and understand about regression. So two cars that differ by 1 ton in their weight would be what? And think about writing a full sentence that makes sense to the reader. Two cars that differ by 1 ton in their weight would be what? What would we say about this? Two cars that differ by 1 ton in their weight would be what? I'll give it another 10, 15 seconds. If you can figure this out, you're really on the right track. So two cars that differ by 1 ton in their weight. If we had two cars that differed by 1 ton in their weight, we would expect them to differ by negative 5.34 miles per gallon, where the car that is heavier is expected to get worse or lower miles per gallon. So two cars that differ by 1 ton in their weight are expected to differ by negative 5.34 miles per gallon, where the car that weighs more is expected to get lower miles per gallon. Does it make sense, Sloan? Like looking at the visualization of it, seeing the coefficient right there, the differences between the two is just showing us right there that we see two cars that differ by 1 ton in their weight, like theoretically speaking, would be expected to differ by negative 5.34, where the car that weighs more is expected, we can't say will, is expected to get lower miles per gallon. Because take, for example, this car right here and this car, the car over here is actually getting higher. Yeah. That's the point. And so you can't say that it will, because these cars over here are the perfect example of cars that don't follow the trend. This is the heavier car, this is the lighter car, and the heavier car is actually getting a higher miles per gallon than the lighter car. But we would expect the heavier car to get worse miles per gallon because of the mostly somewhat linear trend. So that's part of the problem with the non-linearity we saw of the model, and we talked about that earlier, that there's a non-linear trend in this. So the key right there is two cars that differ by, so let's go back to the viewer right here. Two cars that differ by 1 ton are expected to differ in their miles per gallon by negative 5.34, where the car with a higher weight is expected to get a lower miles per gallon. I think we can do a few other things right here. We've got the really nice flex table, and we should be able to go to and do the coefficients or confint. I wonder if I can just put this in a tidy and go to tidy of the confint. No way. Oh, man. Well, can I turn it into a tibble? Confint tibble. Ooh, it kind of did it. Well, not loving it. So can we put it in a flex table now? It doesn't like it. No, sir, it doesn't like it. Well, what happens if we do this? Oop, we got an extra parenthesis somewhere. Data frame. It wants this as a data dot frame. Well, it might have worked. The names are pretty bad right there. The names on that are pretty bad. So we don't want that anymore. We want this. Names are pretty bad on it, and it doesn't have the row names either. So we would have to add in the row names. So where is my formatting? Then let's take a look here at something else. Formatting, row names. Oh, someone already said this. They said, you know, add it to the, so or let's say right here, yeah, variable equals and intercept. That's how we did last week, and slope. And there it is right there. And then we could go here to call names of the data frame equals to variable and lower 95 and upper 95. There we go. Looking a lot better. And then we just take right here and do the call format digits. And looking a lot better. I don't like how it... I liked it better when it didn't put the 95 on the lower line. So I don't know why it's doing that. That bugs me a little bit. Like, I want it to not put it to one. I want it to just do one line. Huh. Well, someone will have to tell me. Autofit? Autofit? What does that do? Let's try this. Autofit flex table. It looks the same. No, it's doing... Ooh. Autofit helped out. Wow, look at that. For our Stat 1 exam, did everyone have a chance to take the exam? I'm sure we will talk more about it. Yep. Everyone, we just have some people who have makeups or have excused reasons. But that is true. Everyone's taking the exam right there. And yeah, so we have everyone taking the exam who should have taken the exam by now. And the autofit looks to, autofit. I got to look and see what that does. But yeah, thank you, Sloan. And this is what we try to do right here in 320 Sloan is we try to make the output look as nice as possible because we don't want to just present someone with information like this right here. Like imagine I gave you a report. Like which of these looks better, Sloan? The information right here or the information, the higher or lower information? Because now we can do really easy things to this. We go right here and go theme. Oh, where am I? I can go theme Vader. Really? And there you go. So we can do a lot of interesting things to this. Change it up. We can put the lines in. But there's a whole bunch of things we can do to this to make it look different. I don't like theme box. A lot of people have been using that lately. Not a big fan of it. Theme vanilla. There you go. There's the vanilla theme. So many things we do. Vanilla theme looks pretty good right there, actually. I'm shocked. I would think theme vanilla would be boring. I mean, it's kind of boring, but Tron Legacy. What? There's Tron Legacy. But we have a lot of themes we can pick from. I wish they added more themes. Theme status, if you want to make it look at a stata plot, which apparently won't let us do. Might not have been part of Flex Table. Oh, it's a GG themes. Yep, it wasn't part of Flex Tables. Wonder if there's additional themes for Flex Tables. I'm going to look for that really quickly here, and then we could do something else. But the point is, when we make reports for 320, we are really looking to make professional reports. Additional themes for Flex Tables. Okay, function, flex tables. No, it might not be additional themes. Flex table gallery. Oh, some people made some really nice flex tables. Using flex tables with ggplot and patchwork. Oh, look at this. This is a flex table right here, and they added the image of the person over to the side. So, I mean, you want to talk about nice looking tables. This is what's possible with R right here. So they've got a really nice, they're adding in the image. So set header, they must be grabbing the URL from somewhere, but there it is. And they show how to do all the code for this to make this, professional. I mean, you give this to someone, or, you could be updating this on a website right here where it's updating the plots at all times. So you can make some, and then they added it to the plot. I mean, that's a lot of, little maybe too much info, but effective high score over here, low effective low score, low effective, wait, did they make a mistake? Low effective low score, low effective high score. Interesting. I wonder who these points are. You can even have it where you hover over and it could like show you the person when you hover over it. But that's really nice plots right there. Maybe a bit too much information. You'd want someone presenting on this, and I'd probably give it to where we could like hover over it and it would show the person. So if you wanted to see, and then we'd probably need some explanations of those. But that's really cool. That's a neat plot. They're showing inserting equations into it, column names. Oh, Mario Kart. Look at that. I got some Mario Kart data right here. What did they? Oh, it's a shiny coin. I was like, what's wrong with that side of it? Really cool. It's very nice data. Kind of relates to 201 as well when we get to the final project, include all that we've learned. Yeah, exactly. I wish we did using R in 201, because here's the thing, there's endless possibilities when it comes to, you can literally sample like the hat and get the color code. You can do that inside of Jump too. There's a lot of capabilities with Jump, but with R, there's pretty much endless capabilities. Technically, with Jump, there is two, because you can do SAS code. So technically with Jump, there's endless also, but I preferably like Jump R because, I don't know, but Jump is more user-friendly, hence why we use it in 201. So here we'll take a look at the data analytics, and then we'll take a break right here. But the data analytics, so let's take a look at that, Sloan. I will go back over here on the main screen. Let's look at some data analytics. Back. Data analytics. Number 5, due on Wednesday, a week from today. Okay. Data analytics. Let's see. We did a lot for 320 right there. 43. Stat 201. Data analytics 5. Got enough time right here. Let's go do it. Here we go. Okay, so this is Data Analytics 5. Make sure you realize I'm going to use a different data set. I'm also going to try to teach you a few things so you can learn how to do regression. So stay tuned, listen in, and follow through with the examples. And as always, look at the rubric. Look at the rubric, and when you are turning in your assignment, make sure you have everything. There's a lot of components right here. It's possible I might not do something super duper thorough, but you want to look at, I try not to do that, but you always want to look at the rubric and be like, okay, write-up is accurate and written in complete sentences in paragraph format. Well, easier one to check off. Statistical significance and interpretation. Report if the linear relationship between price and caret is statistically significant. Define and include the value from the output. Use to support your conclusion. So you got to identify the value. Talk about statistical significance. More on that. Y-intercept interpretation. Interpret the y-intercept properly right there. Very important. We were just doing that a moment ago. Slope interpretation. Interpret the slope properly. The conditions to make sure we're doing a proper regression right there. All 4 conditions listed and explained. I would probably do bullet points for those. You should be fine doing bullet points. I mean, do full sentences. Maybe don't. I don't want some grader to be like, oh, that's not paragraphs, that's bullets. Like, don't do the full report in bullets. But at least for the graders, it's easier when you do those. But one grader is going to not give you points. So maybe you could do them as separate. I guess too afraid a grader is going to get really picky about saying you did bullet points. So write it in a paragraph, its own individual paragraph for conditions. My best advice on that. We have a lot of graders, and we show them how to grade this. Sometimes they're a little picky, and you can always ask us instructors if you feel like the grade was not fair. The appropriate analysis was performed. Correct screenshots. Take a good screenshot. Elijah, good to see you here. Everyone in the future, Brian's using different. Yeah, Sloan right there. Let's pin that. I'm going to definitely use different variables because I don't want to use the same variables as you. I'm not going to do the work. Put your name at the top of the document. Pretty easy right there. So, okay. I think we got everything right here. Not too bad. This is the cost of living data set, not the diamonds data set. So instantaneously right here, I have to make some corrections. Probably Terry's going to make this also. But it's not going to be carat and price. That's a different data set. So this is groceries and restaurant price. So grocery index and restaurant price. Now, the response variable is the thing we're interested in. Like we talk about responses. So response means the Y variable of interest. The predictor is the explanatory. So grocery index will be the what? Like what type of variable will grocery index be if it is predicting? So it's the predictor, not the predicted. So the predictor, I prefer to call it the explanatory variable because it's the what variable. So Sloan or Elijah, the grocery index will be the what variable. The grocery index will be the what variable when we do our analysis. This is key for people getting it correct. It'll be the X. It'll be the predictor, not the predicted. So I prefer to call it, and I'll tell you why I use this terminology right here. We're going to close down those. I like to say we have an explanatory variable because the explanatory variable does the explaining. And we talk about why something is happening, and that is the thing we're going to talk about, and that'll be the response. It took away my nice X right there. So other words for these are predictor. Sometimes we'll call this one the independent. Not a fan of that. That's more mathy. Yeah, that's pretty much it. Predictor, independent variable. So the Y variable is often called the response. That's what I call it. You can call it the dependent because it's going to depend on what X is, mathematically speaking. So when you get the equation, and last but not least, predicted, you can call it the predicted variable. Regressors. So we regress Y on X, right? So is this the regressors? I guess so, right? I don't use the terminology, but you regress Y on X. So you're regressing Y on X. So that makes sense, like in terminology. I think the X, I think so too. It's all in good comments right there. Yeah, it's good to know all the sort of terminology. I just call the X's explanatory variables, and then the Y's, like why is this happening? That's the thing we want to talk about, the response we're interested in. So when you look at this right here, what we're actually doing is we're taking a data set where we have the X and the Y, and we are fitting a line to it. And with this right here, the equation will be Y hat equals B0 plus B1X. And the reason I like this is because B0 is when X is equal to 0. So if you were to look right here at this line and you were to work with it, you would say, okay, wait a minute. The value of B0 is when X is equal to 0. So that's what B0 is. And then the value of B1 is for each 1 unit increase in X, the difference we expect to see in Y. And keywords right there are expected differences. So that would be for each 1 unit difference, what we expect in Y. So let's write down those interpretations right here. Yay! So the intercept has the interpretation. That is when X is equal to 0, we expect Y to equal B, lowercase b, 0. Then we go right here, and slope is for each 1 unit increase in Y, we expect, in X, we expect Y to increase/decrease by B1 on average. Some people are very particular about that on average part. So the key right here, if you notice, is that when we're doing this, it's not about what will happen. It's about an equation that makes predictions. So we almost got it on one line. Perfect. Okay. So you will need to plug in your value of X. You will need to plug in your value of Y. You will need to plug in if it's increasing or decreasing. And you need to plug in your value of the slope coefficient. You'll need to plug in your value of X right here. You will need to plug in your value of Y right here. And you will need to plug in your value of B0 right here. This is the interpretation of the intercept. This is interpretation of the slope. and statistical significance found by looking at the p-value of the slope. If it is below 0.05, we have evidence of a statistically significant relationship between X and Y. Okay, so this right here, Sloan, is pretty much all the notes we need to complete it. This is a very thorough sort of document at this point, having the interpretations and the ability to tell statistical significance. I guess we should write the 4 conditions. Sloan, do you know the 4 conditions right here? The 4 conditions we should be checking, which I think we checked before doing any interpretations. 4 conditions are what? This is for the data analytics, correct? Yep. So the 4 conditions will be what? What are our 4 conditions right here? Is it not going to do a list? I'll do a list the real way. What are the 4 conditions to check? Really? What are the 4 conditions to check? And once again, make sure to use full sentences. And we're basically taking the notes to complete this that we would need to know. And this is the majority of the chapter. There's a few other things, but this is majority of regression right here. We have an X and a Y variable. We have the equation. One thing that will not be used right now is residuals. Residuals is the equation that a residual equals the actual value, which is a dot right there, minus the predicted value from the regression equation. So the predicted values are going to be the y hats, which is the line itself. And then the dots are the actual, like a dot right here is a value of y where it hits over here on the y-axis, where this would have a predicted value over here. So that's the y hat value from the line. Not those good answer. Those are the ways to describe bivariate quantitative data. So that's the way we describe it with strength, direction, form, unusual features. That is the way to describe a scatter plot. We are looking for QQ, which is 2 quantitative variables. We know it in my class as QQ, 2 quantitative variables. Straight enough. No outliers. And plot doesn't thicken. So we got a really good graphic earlier here for plot doesn't thicken. Got to go down here to 1 or 2 documents before this. So with this right here, the plot doesn't thicken right here is we want to see the same sort of strength throughout. The same sort of strength throughout. So if you notice, this is called homoscedastic because it has the same thickness throughout, where this is heteroscedastic, meaning differing thickness, because it's really weak here at the start and then it gets stronger throughout. You do not want to see the plot getting thicker in any way. So what is QQ? How do you know this meets QQ? Like, to make a scatter plot, how do you know things meets 2 quantitative variables? We're actually covering literally everything right now. This notes sheet has the answers to everything once we cover the conditions. How would you know and explain? Like, I would use a full sentence right here and talk about my variables and explain what it means for them to be QQ, which is 2 quantitative variables. Yep, and then basically that, I mean, my X and, I don't want to say too much because I'm too afraid of people copying. Like, I don't want to write down too much. Like, these will be very formulaic, but a lot of your answers for the conditions are not going to be purely formulaic. But, I mean, that's the idea of it, right? They're numbers. But go into more detail on that. Don't be like, explain what 2 quantitative variables means, explain how the condition is met. And then straight enough means we want a straight line to go through the data. We were talking about this a lot earlier, so check out where we were talking about relationships that are not perfectly linear. This right here, we see an issue with the bend in the model towards the end. It's not horrible, but I do see some sort of non-linearity in the model. So when you say straight enough, does a straight line go through the data pretty well? And yeah, mostly. When we talk about no outliers, we're saying there are no points that deviate far from the relationship. So this plot right here is a good example of where there's problems with outliers. The outliers in this plot are going to be over here, over here, over here. And then also we have a little bit of a problem with what in this plot. So this plot, I would say, has 2 issues. It is 2 quantitative variables. Height and weight are quantitative variables. This is a different relationship. But what do you notice also about this plot, especially towards the end right here? We really have an issue maybe with what? What do you notice? All these points are below the line. You want the points to be around the line. starts to curve, so not straighten up. Exactly, Elijah. Great answers, Elijah. That's what we would start to look at right there and be like, it's got a bit of a bend at the end if we were to... No, the line can't bend. No matter what, you'll put a line to the data, but the question is, if you were to fit through the data, which we can do, watch this, you can actually go right here, and I wouldn't suggest putting this in your report, but you can go right here and go to polynomial fit, and it'll fit a bendy model, and look, it does bend it. Now we're going further out than the data, but if you look at this right here and go through only the respect to the data, when it fits a bent model, a polynomial model, it's telling you, yeah, there's a bit of a bend at the end. If we were to bend the model, maybe that would actually help do a better job of fitting to the points. So the line of best fit's always going to be a line, but sometimes we might need to have a what is called higher order polynomial model. So your line will always do a line, but you could look at if you want, like this might be a decent thing for you to check. I would remove it afterwards though, because the grader will be very confused. You would remove this afterwards. So that's got that. So we understand here that we have now fit the line, and we're good to go on that. Now the question becomes, let's go to interpreting the output. So how to get the output and how to interpret the output. So we'll call the first part the overview. Overview. So now we're going to get all the output and interpret all the output. So that's one, data analytics, 5, interpreting output. Okay. So basically you just got a mini lecture over regression right there. Not everything was covered, but in 20 minutes or 15 minutes. Or what was that? I'm going to check. I really need to know. That was a 14-minute mini lecture over regression. Take those notes, learn it. Okay, so now with this right here, let's talk about how to get this output. So to get this output, we need to be in Jump. We need to have the data set downloaded. So we're going to go to our data set. Make sure to go to your data set, as we pinned right there. You'll be using different data than the one I'm using right here. Use your data set that it says to use in the assignment. Now, I'm going to go right here and do Analyze, Fit Y by X. And when I do this, I'm going to choose the Y variable of interest, which is going to be the response variable. Response is key. So if you're looking which one to pick, we're going to try to predict someone's height based on the predictor, or I like to say explanatory variable, of a weight. So once again, this was fit Y by X, analyze, fit Y by X. Let's show the steps again. Analyze, fit Y by X. So go to the top of the screen right there. Hey, Jesse, good to see you here. And then we have the response variable that we are predicting somebody's height based on the explanatory variable or predictor, somebody's weight. We're going to go ahead and click OK, and we get a scatter plot. Interesting. I actually got a nice plot this time. So this is a scatter plot. You might even say here, relationship, height versus weight, whatever you want. Yep, you can rename your plots to make them look nicer, whatever you want right there. And so now we're going to go right here to the red arrow and click Fit Line. Let me zoom in a little bit more so you can see that. We're going to go to the red arrow right here, and under the red arrow, we are going to go to Fit Line. So once we fit the line, it fits the linear model through the data. So this is the linear model. I like to clean this up a little bit. You probably don't need to. Yours might look nicer. I don't like these Q04s. That's just a variable name. And I want to do these to 2 decimals right here. So I'm actually going to edit this. Be very careful. You could have problems if you were to just delete things like that. That'd be bad. So now that looks a lot nicer and is going to be easier to interpret. Great. Good to see you here, Meredith. We got a lot of interesting stuff right here. We're going to go for the most important things. But if you remember from our cheat sheet, which I think we do still have in the background, do we still have our cheat sheet up? Hopefully it didn't. Here's our cheat sheet. The regression equation is y hat equals b0 plus b1x. So y hat means predicted. So what are we predicting right here? What is the y hat? Yeah, great job, Sloan, right there. Good answers. Good, Sloan, thank you for helping out right there. What is the y hat right here? So look, what I'm asking you to do is to line up the equation. I don't think I can get it there. I'm trying to get this equation in line with that, but it keeps, I'll have to do this. Watch this. There we go. There's the equation. Y hat, predicting height based on weight. Do you see how this is y hat right here? This is the y hat. This is the value of b0, and b0 is the slope. And then this is the value of b1, which is the value, oh my God, I just said b0 is the slope. b0 is the intercept, and b1 is the slope. I misspoke. B0 is the intercept. It's when x is equal to 0, which is an extrapolation of this model. It's not a logical intercept. We should add that to comment on intercept being a logical. Comment if it is logical. Should add that right there to make sure people do that, because you sometimes get an illogical intercept. And this is an example of an illogical intercept because the interpretation of this intercept would be, and let's show it right here in the same time as we're interpreting it. So we're going to make it really small right here. So remember, B0 is right here. This is B0. So when somebody's weight, which is x, when someone's weight is equal to 0, we expect their height to equal 49.97 inches. So that is illogical because someone cannot have a weight equal to 0. Next, we have the slope. For each 1 unit increase in weight, because weight is the x variable over here, also down there, for each 1 unit increase in x, we expect height to increase, and that's because it's positive. That's why I said increase by B1 on average, which would be 0.12 inches, because it's in units of inches. Is that making sense right there? So make sure to interpret those properly. Want to make sure to interpret all of those properly. Statistical significance is of the slope, which is down here on the bottom. When you look for statistical significance, it's the p-value of the slope, which you can actually hover over and see the p-value is super tiny. Yeah, Sloan, good work right there. So what we have right here is the p-value of the slope, which is the x variable, is very close to 0 or less than 0.00001. There it is right there. You have to look really closely. It's like 2.65 e to the negative 8. So it's got a lot of zeros after it. But we could say it's less than 0.00001. And this is very, 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 very statistically significant. So this is an extremely statistically significant relationship, telling us that the relationship we see between height and weight is unlikely by random chance. Now, we need to make sure we take good screenshots of this, so be very careful right here. You could take the screenshot of all of this. I could take this right here. And there's one screenshot. Probably make it a little bit smaller. Good screenshot there. And then also we want a screenshot of this down here if we're going to quote the number from it. And this also has the coefficients of the slope and intercept. They're the parameter estimates for the model. And there it is right there. And there's the coefficients. I would make this smaller too. Think about your sizing. Think about how it looks. So if you notice right here, the estimate, so read what this says. It says estimate of the intercept is this, and there's the estimate of the intercept, which is B0 in notation. So that's B0, and this is B1. And the estimate of the weight is this, which is right there. And we did delete some decimals. The statistical significance of the model is the p-value for the x variable, and x variable is weight. So the p-value for the x variable is statistically significant, telling us that this relationship is one that we think is statistically significant, i.e. the relationship between weight and height is unlikely by random chance. And to check the conditions, the assignment the assignment is so heavy on making the model rather understanding, explain. Yeah, exactly. Understanding what the values are. Not so heavy. Exactly. Now, it looks pretty good technically. We'd say here we have two quantitative variables explained in detail. It looks like it's mostly straight enough, like the straight line goes through the center of the data. And there aren't really any big outliers. I don't see any big outliers. We could say maybe there's maybe a mild outlier here. I don't see anything extreme, but I would say it's pretty good. So like at 65 inches, 170, mild outlier right there. So that's just a mild one. And the plot doesn't thicken, is that it stays relatively the same thickness throughout. And so we've checked QQ straight enough, no outliers. Maybe a little thinner at the end, but I would say I am uncertain. This one is not really, like, you want to look for a strong example. We do try to make it more clear when there's plot thickening. So yours right here, when you look at plot thickening, you want to see something much obvious, like more obvious here. So if you don't see anything really exemplifying plot thickening, I wouldn't go with plot thickening. If it looks mostly about the same, which ours looks mostly about the same, then you could say like, yeah, it looks mostly good. Like that's mostly linear. Yeah, mostly linear. If you're really worried about linearity, don't leave this in. You could fit the quadratic. This is a little bend. I mean, it's saying there is a bend because it bends there and bends. I don't know. There's another way to check it. The lack of fit test. It passes the lack of fit test. You don't need to check that. So technically, in the statistical sense, this is fine. This passes the lack of fit test, which what we're looking for is evidence of a lack of fit. It's kind of like a goodness of fit test, but for the line to see if the line is a good fit. I saw the graph you made with homo rather than hetero. So homoskedastic is the good one, which is plot does not thicken, which means same thickness throughout, where heteroskedastic is differing thickness. So in a heteroskedastic plot right here, we see differing thickness. That's got it. And so make sure to walk through, explain to somebody the steps you're doing. We've now covered everything. We did the 4 conditions. We did the slope and interpret its value properly. We interpreted, well, the intercept and the slope. And then we talked about the linear relationship, and we found the value in the output, which told us it was statistically significant. So I think that's got it. Well, I'm going to get ready for class, grab some lunch. But until then, bye for now, everyone. Bye.